Good morning, everyone. I hope everyone is doing very good. My name is Gad, and I will represent myself. So I'm 26 years old, who have a very passion to learn, and I already posted a video explaining what I'm going to do for the next couple of years. So I'm going to learn computer science, and this is the first official video we are going to launch today. In the previous video, I did explain the roadmap which we are going to take, and today I'm going to start with the first course. So as we did explain in the last video, the main page, the main roadmap is OSSU, Open Source Society University, and which they recommend the courses. And actually, before that, I already did take this one. I did not finish it. It's very good for. It's one of the greatest courses for beginners. But with you, I decided to start with this one. It's like 9 weeks, 15 hours a week, but we can do much more. So today it's 8 a.m. So I will try to do like 1 hour of recording. I'll be taking notes. I suggest that you also take notes. I do think they are using a different type of text editor because you are going to learn some programming language in this. It's Python. So I already did this, but I already learned a little bit of Python, but I'm going to start with you, easy. But it's just I am using this this one. It's a Virtual Studio Code, VS Code. This is what they call it, and I found it's more appropriate for me. There is I started with my first was Autumn. My first text editor was Autumn, and I like it very much. But now I prefer doing this because it's fast. So yeah, there's nothing here. There is nothing. You will learn it actually. So let's put this aside and start our first course. Our first course is presented from MIT. It's Introduction to Computer Science and Programming using Python. It's the very basic things. So let's go and watch the video premiere. Video premiere. I don't think that we can use this in English. I do think it's Bromo, yeah. It's like trailer, yeah, I know. So we're going to watch this, and after that we're going to enroll in this course. And actually I want to show you that this course is also available on MIT open course I don't know what do you say, open course website. So you search it in MIT, so you have the lecture videos here, and you can follow everything. It's not long. It's the class of 2016. It's using Python, the latest version of Python. I think it's good version. This is why I chose it. And there is everything here. Actually, I just took this one. I tried on this because I have an account on this, and it's free actually. Only if you want to take a certificate, so you have to pay 67 euro. I'm mixing French and English. It's really, I can speak some French later maybe. I don't know. No, I think this is a bad idea. Bad idea. Stop thinking. Okay. So let's watch this video and we will click it.
Computational devices have become so pervasive that most of the time we don't even realize that we're using them. Computation keeps our planes in the air and our cars on the road. It manages our electrical, communications, and financial systems. It controls everything from homes to pacemakers. And most importantly, computation has changed the way people think about the world. Hello, my name is John Guttag, and I want to tell you a little something about the course, Introduction to Computation and Programming in Python. On the surface, this course may appear to be just another introduction to programming in Python. But if that's all you get out of it, I'll be very disappointed. In particular, you should come away from this course with a good start on understanding how to use computation to solve real problems. The idea is to simultaneously learn Python, how to be a good programmer, and do both of these in the context of solving problems of genuine interest. Now for some truth in advertising. Like all good engineering courses, this course is mostly about learning by doing. We've worked hard at preparing the online lecture material. But truth be told, you'll learn a lot more by doing the problem sets and attempt to apply the things we've talked about in the lectures. If you've never programmed before, you're in for a treat. It may take you a little while to get the hang of it, but once you do, you'll discover that programming is an enormous amount of fun.
So, this is it. As I said, 1 hour. I am really taking notes, guys. So I have to bear with me. Maybe in the next videos I will record myself taking notes. I don't like to be. I don't like to show my face for camera. But I do think I can manage to have a shot for me studying with you. So, as I explained, it's time to study and enrolling. Let's go. I'm very, very motivated actually. I love this. I love doing this with people. I do really enjoy it. So this course is I did start with it, and before I decide to share my knowledge with you, and that's it. I'm not going to donate, so no. Oh, yeah. So let's view course. I always keep YouTube window next to me, and the original course. I don't know, and I do use sometimes a translator. So Google Translator, it's like this. Yeah. I do use Google Translate because my original language is Arabic, and I do speak French and English. So I do change between them if I needed something. So, well, actually. You will not have access to the exams. Yeah, as I explained before, I don't care for the exams. I do just want the knowledge. I do think the knowledge is the most important thing. So here we have. Yeah, I'll try to shift that a little bit. I don't think it's important to see it because Yeah. So this is like the guidelines and the dates of yeah, beginning, ending of the exams, and the minimum time for uh, maximum time for finishing, and they like stick to if you don't aim for a certificate. So we are like, well, a little bit on schedule. We're a little bit behind, so we have to be careful. So yeah, now I am going to jump in, and I hope you the best, guys. Let's do it. Have fun. We can do the ADX. Expand all. I want to see everything. So. Week 1 Python basics. And week 2 to programming. I like to read. I like to read the topics. I don't know. I do think I have this ego to see what's in front of me. Maybe I don't understand anything, but like I would like to hit it, like really see everything, and imagine that I do speak of myself, but it's like for me imagining it's very difficult, but I can crack it. Let's go. So I do have all my pencils and my take notes. Let's go. I'm just repeating the same stuff. I do think I already make yeah, there, this is it, there's it, it's here. Yeah. So if this is your first yeah, next I don't need it. You can try it if you want. It's a demo for how to get used to EDX. I'm sorry, EDX. So option digital learning. Welcome to online courses. Blah 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 blah. Next. I don't think there's anything. Downloading Python. Ball operating Windows. Submit. coding experience. Well, actually, I will be absolutely none. So it's a ball. I don't think. Yeah. So how the same thing I told you before. Here in the course, they are using something called Anaconda. It's a text editor. For the people who have no clue what a text editor is. Text editor is this. So technically, you can write whatever you want, and you can after that just choose the what is it. So you want to be a text like txt, or you want it to be a Python script, or you want it to be a JavaScript, JavaScript, or you want it to be an HTML. So you defined it when you hit this, when you hit this. So I already save it like first b.by, and it's been saved as a Python. So this is the text editor, not more. So you have to trust me now, understand this, and after that everything will come along. They will teach everything here. I do advise you to follow them because they are the real teachers. And the whole page here is for downloading Python and a text editor for understanding everything in the course. So, how about the word cloud? I don't think. Yeah, I don't care for your course philosophy, I think. Yeah. I'm sorry, but it's reality, no? So, research to help you succeed. Yeah, this is a very, very good. Yeah. So let's take it one by one. So official Python 3 documentation. Documentation is, for people who don't know what is documentation, it's the language, the dictionary of the language, everything you want in the language. There is no one can teach you everything. So eventually you will learn the basics, you will learn how to search, and after that you will learn what to search when you want something. Like for example, if you're programming for a mathematical formula, you will understand how to search for typical one type of um, argument or objects or functions, or or loops. And after you search in the documentations. So yeah, look, this is the Python. It's finished. This is it. But it's actually it's very, very long. For example, like this. I don't know what is it. But for example, objects, multiple dimension arrays, multidimensional arrays. Like this will help you. So you type something, and voila, sets, frozen sets. Like this. So this is very important. Eventually you have to read this, and I did start with it but didn't finish it. It's really long. So official Python 3 documentation. We already know what's BB8 style guide for Python code. You got good and bad style in Python. So do you think it's a Wikipedia? I know. Pip 8. What is this? It's a library, so uh, you can also read about this. I don't think I don't think I'm going to use it. So textbooks will help you. Yeah, eventually it will help you, but I do recommend. I do recommend to focus on one textbook. I can tell you which one because it's not important which one. You choose a book, you go with it. You know, I go with one book. I did read it, and I did some cake programs with it. And but actually, I stick with it. You can do whatever you want, and yeah, and I do think you can find it for free. So just type anything on you Google, and it will give you a PDF, and will give you a free PDF version of the book. Tutorials. Tutorials. There's a lot of tutorials. Also, I do. Uh, uh, um, Prefer to you to choose also one tutorials and go with it. For example, this one I don't defining for example defining function. So you define function like this. You have to read everything, but stick with it. Don't change your mind. No, it's not important which one. It's like the textbook. Debugging. This is software like um, I don't know. You're going to Python tools for Visual Studio. I don't know what it is, but like let's check it out.
Project template. I'm just going to go ahead and click OK. And I can quickly play around and discover what I want to do with Python code. You may already be used to using the REPL from the command line, but one of the nice things about using it inside of Visual Studio is the improved features that we have. So for example, in addition to normal class and 100,
Yeah, Visual Studio. I don't think it's going to help us.
and now we know that the result that's coming back from that is actually an integer. So I'm getting
I
all
don't
of my
think.
integer completions here. And if I were to hover on,
I don't think that very important now. Yeah, yeah. This is the one. Yeah, look, Stack Overflow. If you don't know it, you have to. So it's Stack Overflow. I'm showing the Stack Overflow. Okay. It's the like how can we say the paradise or for everyone. It's the paradise of programmers and developers. It's everything you can. It contains everything you want to search of. It's literally everything. So there's a very good people here, very very nice people who can help you solving problems, because eventually to be a computer scientist you are a problem solver. So for solving problems that stuck with you for a long time, eventually you can ask for help here, and the people are very very nice. For example, let's take this. I am working on a model creation where multiple uh, senior excuse me, I don't know what this word is. Sensorious inside the Excel sheet will be compared using string similarity sheet with serious. This sheet finally create a model using some logic extra, and like you can see there's there's people who's responding on him and working out the problem. I don't think they there is people responding on this one. I don't think this one is. How to efficiently reorganize dictionaries in Python. So like there's someone who just replied, so you can write a reply or write a question. So this is very good. This is good. This is good. You can go and solve problems, and that's nice actually. This is a Python mathematical problem. This is you will use Python for I do think yeah yeah, this is the one. So you will use Python as a programming language to solve mathematical forms like equation and stuff. Yeah, I do think it's like this. Yeah, it's like this. And project Earl is very nice also. Well, you have to check this out when you enter the coding path. I don't know this one. Yeah, it's warming up. It's in Python too, but like you can do it. Code Wars. What is this? Code Wars. Okay, sugar scale. Okay, so it's a game war or something. You will use programming language to solve challenges. Nice, very nice, very nice. I like it. So I'm going to hide this session. So this is here. They are like explaining the grades and like I don't care. Let's jump in. Let's jump in. First lecture, yeah. So I hope we can do this. Actually, there's something. I am not going to give answers for the questions or the project in the course. So I'm just studying with you. When I solve the course, for example, this is a video. This is a video, but this is an exercise. So I am not going to reveal the exercise, the answers of the exercises. Eventually, this is a very low range, low difficulty questions. I don't think it would be a problem, but when we progress in the course, the programming challenges would be the classified. It's a very serious, very serious adjective. So it's not classified. It's just like I'm not going to show you how I'm going to solve, because I want you to learn how to solve this problem. This is what we are going, what we doing, learning. So you have to learn by yourself, and if you face a problem and you can start to ask people, you can always actually you will get frustrated before starting this first lecture, because I'm not going to speak a lot after that. You will get very frustrated, and you will have like maybe some minor depression because you can't solve these problems, but it's normal. This is what we are here to do. This is the main roadmap. This is the greatest things to have. To be very sad because you are not able to accomplish this solution, and this is the beauty of the thing. You do care for learning, you do care for finding a solution, so this is what give you the benefit when you get the solution, because you're going to get it in the end. So trust me, really trust me, you're going to do it. Everyone, trust me, you are going to do it. And I hope the best for you. So, first lecture, have 30 minutes gone, and we have 30 minutes. So, that's great. Let's go.
Welcome to 600, Part 1. We're delighted you're going to join us for the next several weeks as we explore interesting issues around computational thinking and programming. Now, what are we going to do in this course? What do we want you to take away? At the end of this course, what is it we'd like you to have in your armamentarium of great problem-solving tools? We're certainly going to teach you about programming. We'll teach it in a particular language called Python. But more importantly, we want you to start learning how to think computationally, to think algorithmically, to think like a computer scientist. And what does that mean? It means we'd like you to think about, when given a new challenge, how can I get the computer to solve this for me? How can I describe the stages I want to use to get this done in such a manner that I don't have to do it, I can get the computer to do it? That's the notion of computational thinking, of algorithmic thinking, and that's what we're going to try and teach you about in this course. Now, that means you really want the computer to do the work for you. It's going to be your servant, and that means you need to think about how do you get it to do the things you want it to do. To do that, we're going to cover a range of topics, and we'll see all of these over the next several weeks. We want the computer to compute something for us, infer some new knowledge for us. That means we have to think about how do we represent that knowledge. And we'll do that with particular things inside the machine called data structures. We want it to infer new information or define information, and we're going to see there are standard tools for making that happen, things called iteration and recursion, and we'll come back to those over the next several lectures. A big part of what we want to do inside the computer is to have
The quick note for everyone, don't worry. All this, I think they are going to teach us what is it, and when I heard it the first time, I was like, what is this? But now I'm pretty sure they are going to teach us very well.
have it be able to deal with things in a manner that we can see and understand. And that says we're going to use the notion of abstraction to capture elements and then treat them as if they were primitives and reuse them. And that leads naturally to the idea of modularization, creating modules, tokens, elements that we can stitch together to come up with solutions to problems in interesting ways. Once we started learning how to build algorithms, to think algorithmically, we're going to see that there are standard classes of algorithms. And we're going to use those for common problems like searching and sorting. And we're going to see as well that different algorithms have different costs. And we want to see how to use that to reason about the expense of doing something and better ways of finding a solution to different problems. So here's our roadmap. These are the things we're going to deal with over the next several weeks as we talk about and get you engaged in computational thinking. If we're going to get the computer to do this for us, though, we could start by asking, so what does it really do? Boy, that sounds like a dumb question, right? Of course, computers do all sorts of amazing and awesome things. They can play Go. They can find things on the World Wide Web. They can do all sorts of wonderful, marvelous things. But fundamentally, a computer really only does two things. It performs calculations. Well, duh. But in this case, the calculations are actually very simple things. Turns out they can do them amazingly fast. But all they really do, they perform calculations and they remember things. Early computers didn't have much of this power. Modern computers have a lot. But those are really the basis of them. Perform a lot of calculations really quickly and remember results. Now you could ask, how fast is it really in terms of performing calculations? The machine you're using can probably do about 1 billion calculations a second. And just to put that in context, if I had a lamp sitting on my desk here, about a foot above, and I hit the switch, by the time light went from the bulb to the table, your computer's performed 2 operations. That's amazing. It's really fast, and it sounds like that's going to let a computer do almost anything. How about remembering things? Depends on the size of your computer. You probably have a few gigabytes of memory in there. A big computer or something on the cloud might actually have hundreds of gigabytes of storage. What does that say in terms of what it can hold? Well, if you took the standard novel and you put it inside a machine, a typical machine could hold about 1.5 million books of a standard size. So if you're going to start reading those great classics now, it's going to take you a while before you get through all the things that are stored on your machine. So it sounds like computers are amazingly good, even though they only do simple calculations and they remember results. Hold that thought, because we're going to come back to it. Because we can also ask, well, what kinds of calculations does the computer actually do? Every computer comes with a set of built-in operations. These are typically primitive arithmetic operations, multiplication, addition, division, and simple logic operations, comparing true and false values in order to make decisions with that. If that's all we had, that's going to be a real pain. And so what we want to do through this course is figure out how to define new calculations, new operations, things we create and give to the computer so that it can abstract them, encapsulate them, and treat them as if they're primitives. But to start with, the computer simply performs a lot of those calculations, those simple primitive calculations, very quickly. Is that enough? Might be. If that's the case, we really don't have to do a lot in terms of computation. And I want to give you a couple of examples to show you why, even with the speed of modern computers, you need to be able to think carefully, cleverly, algorithmically. Here are two obvious examples of things you might like to do. You want to find a piece of information on the web, something you do every day with a search engine. You might want to play chess or have your computer play chess for you. Suppose you want to search the web. How much could you do if you just were using simple calculations? Well, here's a little computation I did before I came in to capture this lecture. There are about 45 billion pages right now on the World Wide Web. On average, there are about 100 words on a page. And for sake of argument, let's assume if we want to find a word on a page, it's going to take us about 10 operations to try and find that, whether that word is on that page or not. We'll see later on how we could get it down to about 10 operations. That says, if I'm going to just brute force try and search everything on the web to see if I can find the thing I'm looking for, it's only going to take me about 5.2 days to find something. You probably don't want to wait that long. So even with a very fast machine using these simple calculations, it's not going to be enough. How about playing chess? An expert will tell you there are about, on average, 35 moves for every setting on the chessboard until you get to the end game. Suppose you want to look ahead 6 moves in order to try and decide what you want to do in order to beat your opponent. That says you've got about 1.8 billion boards that you need to check. And if it's going to take you, for example, 100 operations for every choice, it's going to take you about 30 minutes to decide each move. Probably too slow. And this is simply a way of saying that even with fast computers, we need cleverness, we need algorithmic thinking to take those simple computations and turn them into something more powerful. And that says good algorithm design is going to be crucial, and it's one of the skills you're going to learn throughout this course. What about storage? Got lots of storage in a machine. Why don't I just compute everything once, store it away, and then just look it up? So let's go back to chess. Imagine I just want to look at all the possible chess games and store them away so that when I'm in any move, I'll just know what I'm going to do in order to get to a winning position. Well, experts would suggest that there are something on the order of 10 to the 123 different possible chess games. That's a really big number. And in fact, there are only about 10 to the 80th atoms in the observable universe. So there's no way that we can store all of that information away. And again, it comes back to saying we can't just use brute force or pre-compute. We need to be clever about how we come up with solutions. Even with that, we're going to ask, are there going to be limits to computation, even if we can build clever algorithms? And in fact, one can suggest that there are still some limitations to what a computer can do. Some problems are still, at least at the moment, too complex, even with clever algorithms, to come up with solutions fast enough. I'd love to know what the weather's going to be right in my neighborhood every morning before I get in my car to come to work. I just don't have enough data and enough compute power to be able to model at that level of scale. Maybe eventually, but not yet. In some cases, the fact that some things are too hard to compute actually works in our favor. And encryption schemes are an example of that. Things that you want to store on a computer encoded so nobody can break them rely on encoding or encryption schemes that in turn rely on the fact that some problems are simply too complex to be solved by a computer. And in some cases, even if the computers get faster, it's still not going to be possible to solve them. Some problems are just fundamentally impossible to compute. And a classic one from computer science is called the Turing halting problem. And it simply says, if I want to write a piece of code, a program, that could take as input any other program and tell me whether it will always work, whether it will always stop with an answer, it turns out you simply can't compute that in all cases. So there are going to be limits to computation. But not to worry, there's going to be a lot of things we can do, and that's what we're going to do throughout this course.
Nice. Very nice introduction. I like it. So next video. Let's go. Oh, that seems serious. Don't forget, guys, taking notes. Let's go.
Okay. We want to start thinking about how do we get a computer to do things for us. So we can start by saying, well, what do we want a computer to do? We want it to compute something. Sounds like a deep philosophical question. And in fact, it is. And that leads to an even deeper philosophical question, which is if we want a computer to compute something, we can ask, well, what's the knowledge that it's going to use to do that computation? And that actually leads to an interesting distinction, because we can divide knowledge into two types, what we're going to call declarative knowledge and what we're going to call imperative knowledge. Declarative knowledge, those are statements of fact, statements of truth. For example, if I were lecturing here at MIT, I might have gone in ahead of time and strapped some or taped some candy under one of the chairs inside the lecture hall. An imperative piece of information simply says, there's candy taped to the underside of a chair. It doesn't tell you anything about how to find it. It doesn't tell you where to look for it. You'd either have to do it in parallel by having every student reach under the chair or search the entire lecture hall. It's simply a statement of fact. Imperative knowledge is a recipe. It's how-to knowledge or how-to information. And this gives us a sequence of steps to find a solution. Again, if I stuck candy under a chair inside the lecture hall, I might say to the lecturer, do the following. Face the students at the front of the room. Count up 1, 2, 3 rows. Start in the middle section left side, go in one chair, look underneath it. Candy is there. It's a recipe. It's a sequence of how-to steps, very mechanical, to get things done. Those two kinds of knowledge are important, but only the second one's going to really be of value to us, because that's what's going to help us get the computer to do something for us. To see it, let's look at a simple example. Suppose I want to compute the square root of some number. To make it easy, I'm going to start with just an integer number. Here's a statement of fact. The square root of the number x is that y such that y squared is equal to x. And I'm just going to highlight it right here. There it is. There's a statement of fact. Does it tell me how to find a square root? No. If somebody gives me a good guess, I can use this to check. So if I'm trying to find the square root of, say, 16, and somebody gives me a guess of 4, I'm lucky, because I can say 4 times 4 is 16, and I'm done. But it doesn't help me find something. Here's a version of imperative knowledge. And this is actually a very old algorithm. It's attributed to Alexandria of Haran, dating back into the 2nd century BC, though other people suggested it existed earlier than that. But here's a recipe for finding square root. I'm going to start with a guess, and I'm going to call it G.
Very nice.
If G times G, if G squared, oops, sorry, I'm going to go back. If G squared is close enough to X, then I'm going to stop and say G is the answer. Otherwise, I'm going to create a new guess by taking G and X divided by G and averaging them together. Take the average. Okay? Once I've done that, I'm going to repeat. I'm going to go back up and do the same thing again. And that's going to give me a little algorithm, because it's going to let me now say, start with a guess, check to see if the guess is close enough, and if not, keep going. And you can see that at a little graph at the bottom. I start with not a very good guess. G is equal to 3. I square it. That's 9. 9 is not, as you can see here, very close to 16. So I'm going to take X divided by G is right there, and I'm going to take G, and I'm going to average them together to get a better guess, right there. With that better guess, I'm now going to do the same thing. I'm going to go back through that loop, go back up to step number 1, and say try it again. And you can see the steps here. I square 4.1667, I get 17 and change. It's really not close enough. I take x divided by g, I take the average of x and x divided by g, and I get a much better guess. And you can see after the next round, I get a guess that's close enough, I'm probably ready to stop. So, this is a nice example of a little algorithm. It's a little recipe. And let's capture those pieces together.
Nice,
What's a
nice,
recipe?
nice. Wait. I am
3 pieces.
going
It's a
to
sequence of simple steps.
try to do it
So,
on my own. So, guys, let's okay, that's very ugly face.
this is a nice...
Okay, that's now it's more convenient. So, the algorithm says, like, if what's the square root of number? No, not this. Yeah, this is the square root of number. So 16. Okay, 16. So we guess a number. It's a 3. We multiplicate by itself. If it's the number, well, it is the number. If it's not, we'll try to divide the original number on it, and after that we will take the average of the division here and the guess that we took, and the average is always the sum on the divided by the number of the sums, the number of the sums. Yeah, I think I can say that. I don't know, so I'm sorry if I'm saying it wrong. So and we repeat the same thing until we have one number. Yeah, nice.
This example of a little algorithm. It's a little recipe.
Very
And let's capture those pieces together.
very loud.
What's a recipe? 3
Very loud. I'm
pieces.
sorry.
It's a sequence of simple steps. It's a flow of control, a process that's going to tell us what order in which to
I
execute
noted
the steps.
actually.
And it's going to give us a way of deciding when to stop. So those 3 pieces, simple steps, a sequence of things I want to do, a checklist. A flow of control, a thing that tells me when to go to the next step, when to jump to some other place in that sequence of steps, and a way of deciding when to stop. Those 3 pieces constitute an algorithm. And you just saw it in the little square root example. In general, the flow of control was going successively through the steps until I got to a test, and that test had me jump back to another place inside the algorithm. That's what an algorithm is. That's what a recipe is, and that's what we want to capture.
Nice. I have 2 exercises, and after that I am going to. I don't think I'm going to do this, but I am going to solve this 2 exercise, and after that I think I'm going to stop because I have to go to work. It's 9:50, so I have like 15 to 20 minutes to go to work. I'll try to solve this fast, or I'm going to solve them now. So guys, very nice to have you with me here. It's been a very nice journey today, and please do every YouTube algorithm for me. That would be nice. And keep on the good work. Try to advance a little bit to achieve more stuff in the course, and we will meet in the evening. I hope if I'm not so tired, I do come back really tired from work. So I don't know. Maybe tomorrow morning we will do another hour before work also, and that we can finish this and the course. Let's see the course. Let's make for example let's do schedule, you know. So this is the first one, the second one, third one. Maybe tomorrow we will finish this and this in the same time, and after that I can solve this on my own. So maybe tomorrow we'll have time, 1 hour. I think it's very good to finish these. Well, I hope you enjoyed. You enjoy this little bit course and introduction. So yeah, we're going to be computer science guys. Have a nice day and bye bye.